Okay, so I'm checking you can still hear me. Thank you to student Mu for passing host to me. I think we are recording again. Okay, let me know if you have any problems. Thank you. Okay, so f is concave down because the second derivative is negative, and concave up for 0 to infinity, just in the graph we saw before. And giving another example, fx is 1 minus x squared. F prime x is minus 2x. And f prime prime x is minus 2. So in this case, the second derivative is negative. So f is concave down for minus infinity to plus infinity. And if we draw the graph, then as usual, the curve of the graph is pointing down, so concave down. Ah, thank you. Can you hear some music playing? Yeah. Is that coming from inside the room? I don't know. Okay. Yeah. Okay, so definition. So if graph has tangent line at a point where concavity changes, we say this is a point of inflection. So note means f prime prime positive on one side of point and negative on other side, which implies that if f prime exists at point, then it is 0. So why is it, if you remember the intermediate value property of derivative? Therefore, at a point of inflection, oh, I'm sorry. I mean, if f prime prime exists at this point, it is 0. So let's just draw some pictures of the graph of f prime prime. It's either going from positive to negative, or from negative to positive. And if it exists in the middle, then it must be 0. But it might not exist. I'll give an example in a moment, so this will make more sense. Either f prime prime has to be 0, or f prime prime undefined. So on a new page, let's give some examples. So if I have fx equals x cubed, like this, then at this point, I have, well, I've not drawn this very well. I need to have a horizontal tangent here. Like this. So here, a horizontal tangent but also, if I take fx is x to the 1 over 3, so the cube root function, like this, like this, then I still have a tangent here, a vertical tangent line. And we're going from concave up here to concave down here. And the same in this top example, but I won't write it down because we've said a few times. But in both cases, we have a point of inflection, in a sense. And if you want to test this, so if I calculate the derivatives, f prime x is 1 over 3 x to the minus 2 over 3. So that has an infinite limit, as you'd expect from that vertical tangent. And f prime x, when I repeat the differentiation, I get minus 2 over 9 x to the minus 5 over 3. So this is also undefined at x equals 0. But it goes from positive to negative as I cross 0. So that's why we have a point of inflection there. So note, if f prime prime c equals 0, we do not necessarily have an inflection point. So in the first example, there is an inflection point and f prime prime is 0. Let's just write it in. So f prime prime x we calculated before is 6x. So it's 0 at 0. But an example when we have f prime prime is 0, but no inflection point is if I take fx is x to the 4, and then in the same way, f prime x is 4x cubed, and f prime prime x is 12x squared. So that's 0 at 0. But the graph of x to the 4 does not have an inflection point. It's concave up. I mean x squared. F prime is greater than 0 for all x. So concave up everywhere. Right. So another application of second derivatives. So if we can calculate the second derivative, it helps us spot extrema. So take f prime prime continuous on an open interval containing C. Then 1, if f prime C is 0 and the second derivative is less than 0, then f has local maximum at x equals C. And in the same way, if the derivative is equal to 0, but the second derivative is positive, then f has a local minimum at x equals to C. But careful, if f prime C is 0, but the derivative, the second derivative is also 0, then we conclude nothing. There may be local extrema, or maybe not. Okay, so let's give some examples of how to apply this. So a simple example. So fx is 1 minus x squared. We know that has a local minimum at 0. So f prime x is minus 2x. So we can find the critical points. We set f prime x equals to 0 and solve. We just get x equals 0. And now this test is telling us to calculate the second derivative at this point. Well, the second derivative is constant, it's minus 2. So from the first bit at the top of the board, so local maximum. At x equals 0. Okay, So that's one example. And for another example, x to the 4. So here f prime x is not 3, but 4x cubed. So critical points, again, we take the derivative is equal to 0 and we solve. And we get x 0. Excuse me. But now, f prime prime x is 12x squared. F prime prime at this critical point 0, therefore is 0. So test says nothing. Even though fx has local minimum. Actually a global minimum at x equals 0. Okay. So a few more minutes. Let's see what to start. Okay, let's do this example. Maybe we won't finish it. But we can put all these techniques together to sketch a lot of graphs. So strategy. First we find extrema. And then we find increasing or decreasing regions. And then we find concave up-down regions. And then we can sketch graph. And fit between known points. So let's give an example. If I have y equals x plus 1 squared over 1 plus x squared, then I start by seeking the critical points. So I take the derivative. So this is a good example in the quotient rule. Remember b, then the derivative of that is vu prime minus uv prime over v squared. So y prime is 1 plus x squared times 2x plus 1, chain rule, minus, this is going to be uv prime now, x plus 1 squared times 2x all over 1 plus x squared squared. But this is going to simplify. I can, well, not fast enough apparently, but okay, we'll continue this after the break. Okay, so I completed the calculation in the break. It's just rearranging this, but you get a nice answer at the end here. 2 times 1 minus x squared over the square of the original denominator. And so we see that we have, if I set y prime equals 0, because the numerator is always positive, this is true if and only if 1 minus x squared is 0, so if x is plus or minus 1. So critical points at minus 1 and what's the value at minus 1? The value at minus 1 is 0. And the value at plus 1 is 2 squared over 2, which is 2. So now we want to know if they're maxima or minima. So we calculate y prime prime. And this is just by the same method. We use the quotient rule for a derivative. And let me just give the answer, because otherwise it will take me some time. And this is in the book as well. So we get 4x times x squared minus 3 over 1 plus x squared, now with a cube. So let's evaluate at the critical points. At the critical points, we get y prime prime is, if I put minus 1, I get 4 times minus 1 minus 2 over 2 to the power 3, yes. So I get a plus 1. And at the other critical point, I get a minus 1. So it's by the same sort of calculation. So we have a minimum and maximum, respectively. Okay, so we know they have these 2 critical points. What else do we know about the function? We also have an asymptote. Because we can write y, we defined it to be x plus 1 squared over 1 plus x squared. But we can write this as 1 plus this fraction. And that goes to 1 as x goes to plus or minus infinity. So as x goes to plus or minus infinity, this bit goes to 0. And now we can also see the concavity from this function y prime. So for x is less than minus square root of 3, the numerator of y prime prime is negative. Concavity is down for this. Did I get that right? Okay, I might have to check this because it's confusing. Yes. So in that case, x is negative and x squared minus 3 is positive. But it's up for x in this interval, and then it's down again for x in this interval, and then up again for x greater than square root of 3. And all these things you can see in the graph. So let's copy in the graph now. So we see the two critical points first, one at minus 1, 0, and one at 1, 2. And we have a horizontal asymptote, the horizontal line, and we have that the graph starts concave down, curving down. It's concave up. Let me write that one in because it's a nice obvious one. We have concave up. Very clearly on the graph, concave up. And then here, it becomes concave down. And you can see the point of inflection where it changes from concave down to concave up here. So all of these features of the graph are shown by the derivatives. Okay, so we've done a lot of work on graphs and their properties. And it might not be obvious why that's useful, but it's extremely useful because once we can do all these analysis of a graph, then we can solve lots of practical problems. So that's the subject of the next section here. Problems of optimization, making something the best. Means finding best value of a dependent quantity. So for example, minimum cost, maximum size, or speed. It could be minimum cost or minimum time. All of these things are optimization problems. So we'll give a few examples. So let me put in a picture to explain. So a problem we talked about at the beginning is if we have a box that's made in this way by taking a square. We had a rectangle before, but in this case, let's take a square and let's cut squares into the corners and fold up to make a box like this. So in this case, the thing that I want to optimize is the volume. And I optimize that by changing x to give the largest possible volume. So the volume, looking at the second picture, is the 3 dimensions of the box multiplied together. The height is x, and the width and the depth are both 12 minus 2x. So this is the volume. And then I want to calculate dv by dx to find critical points of the volume as x varies. So dv by dx, by the product rule for differentiation, 12 minus 2x squared plus x times the derivative of 12 minus 2x squared. So we make that with the chain rule. We get this. So here I'm using chain rule. And then I can try and simplify this. I can take out the 12 minus 2x. So in the second term, I'm just left with minus 4x. So gathering terms, I get this, and I can take out a 2 and a 6. To get this. So now, domain of function v of x is, well, x can be as small as we like, although I don't want it to be 0 because then the box wouldn't have any volume. and it can go up to 6. That's half the width of the original square. So seek a local maximum. We seek the global maximum in the end. So seek maximum of function. So remember from before, we check at endpoints and critical points. So what are the critical points? So dv by dx equals 0. From that expression we got happens if and only if x is 2 or 6. So 2 is the only critical point in the domain. So calculate value at x is the endpoints, that's 0 and 6, and x is 2, the critical point in the domain. And we get values 0 and 1, 2, 8, and 0 again. So this 1, 2, 8 is the global maximum. And that happens at x equals 2. Okay, so going back to the box, so the box is drawn here turns out to give the maximum possible area, maximum possible volume. I mean, if you imagine x equals 2 in that case, that's the maximum volume of the box. So another example. Start with the picture. So if I take a rectangle inscribed in a semicircle radius 2, and by the way, that means that the corners of rectangle they lie on semicircle. So question, what is maximum possible area? So in the picture, it's drawn the rectangle going between minus x and x, and that rectangle is going to have a height square root of 4 minus x squared because of the equation of the circle. So that's what the picture is showing, and it means that the area AX is 2x, the base, times square root of 4 minus x squared, the height. And then dA by dx is, I'm using the product rule here. It's 2x times the derivative of the square root. So using chain rule, I'm going to get minus, well, let me write it out like this. So minus 2x times 1 over, 1 over 2, 1 over the square root of 4 minus x squared. So this here is another use of the chain rule. And then continuing with the product rule, I get the derivative of 2x, which is 2, and I keep the square root of 4 minus x squared. So if that is 0, the condition to have a critical point of this function, then it has to be that minus 2x squared plus yes. I want to check I've got the 2's right here. It should be this. So why does this work? Well, I can cancel these 2's. And then the first 2 and the second 2 in this equation become the first 2 and the second 2 in this equation. That's right. Okay, and then this is if and only if I have 8. Okay. I have 8 minus 4x squared equals 0. So that happens if x equals square root of 2. That's the only critical point in domain. Because what's the domain? Well, we want a rectangle, so the domain is from 0 to 2, not including 0 or 2. So again, we evaluate values of AX at the endpoints 0 and the critical point square root of 2, So at the endpoints, the function gives 0. And at square root of 2, it gives 2 times square root of 2. And 4 minus x squared then is 4 minus 2. So this is 4. So going back, what's the area of the semicircle? Well, that's half pi r squared, which is 2 pi in this case. And that's something like 6.3. So you can see we can get 2/3 of the area of the semicircle in an inscribed rectangle. And we'll see, if you look in the book, there are many more examples like this. So from physics and economics, biology, medicine too. But for now, let's just leave it at that. And go to a new topic. Another application of derivatives. This is called Newton's method, and it's a method for finding roots of a function f. So idea. Let's start with a guess. x0 for a root. So say the graph of the function is something like this, and we have our guess x0. Then how to get closer to a root. So in this picture, we can see from the shape of the graph that the root is less than x0. And that's because the graph is increasing at that place. So a way to find my root is to take a tangent line at the point x0, and find where that intersects the x-axis. So let me write that. Take tangent line at x0, fx0, and find the x-intercept. So that brings me closer, and we can get even closer by repeating this process. So, say this is the function f of x. The tangent line has slope f prime x0, and it's through the point x0, fx0. So equation is y equals fx0 plus f prime x0 times x minus x0. X-intercept, as usual, we set y equals 0 and solve. So what do we get? We get x equals x0 what do we get? So yes, x0 minus fx0 over f prime x0. So substituting that back in, do we get the right answer? Yes, we do. And so we take this x to be x1, and we repeat to get x2, 3, and so on. We hope that these will get closer to the root. So what's the procedure? Step 1, guess x0 close to a root of x. maybe using a graph or some other method. And 2, calculate x1, x2, and so on using this formula. So for each xn, I do what I showed above. Use this formula to make the next x in the sequence. So note, method fails if f prime xn is 0. That is, have a horizontal tangent. So let's give an example. If I have fx is x squared minus 2, so we know that this has 2 roots, plus or minus square root of 2. And we can use this method to calculate them very accurately. So what do we get? F prime x is 2x. And so the formula says x n plus 1 is xn minus xn squared minus 2 over 2xn. So we can simplify this, and we get xn over 2 plus 1 over xn. So it's quite a simple formula that gives you your new values. And if you use this to calculate, where are we? Yeah. So if I start with 1, so if this is my guess, 1 that I start with, and I use this method, this is the result we get. So if I put 1 as x0, oh, is the book using a different convention to me? No, okay, so I was saying you guess x0, and then x1, we can use the formula, is 1 over 2 plus 1 over 1, which is 1.5, and then we use the formula again and get x2, which is something like this, and we keep on going. But even after 3 steps, we are very close to the right answer. The error is only 0.00001. So actually this method a method often used in computer algorithms. So when you ask a computer to calculate a square root, this is probably what it does, because it only takes a few calculations. It's very easy for a computer to get lots of correct digits. Okay, but note also method may fail. So it's easy to make an example of that. So graph fitting in a parallelogram as follows. So if I have the x-axis here and a parallelogram like this, I need to draw a bit better. Parallelogram like this, and my graph goes need a tangent there. My graph goes like this, and then let's call these points A and B. Then if I guess x0 is equal to A, so you can see from the graph, the tangent at that point A has an x-intercept at B. So x1 is B. But you can also see from the graph that the tangent at B has an intercept at A. So x2 is A, and so on. So if this is C, so we never find the root C. Okay, so it's only a few minutes left, so I don't want to start a new topic, but let me say next time we'll talk about antiderivatives. So, oh yeah, or I can go back and show part one of the procedure. Part one of the procedure is just make a guess. So the procedure works best if you start very close to the root. But even in this case, in the example we did, we're about half away from the root, and still the procedure works very well. Okay, so let me just finish by giving the definition of an antiderivative. Definition F is antiderivative of F if the derivative of F, big F, is little f. And these are very useful just like derivatives. So we'll talk about that next time. Thank you.